Welcome everybody to section 7.4 here in Algebra 2, adding and subtracting rational expressions. Now, we've been talking a little bit about how rational expressions are really just acting like big fractions, except they have, binomials and other polynomials acting as numerator and denominator. Well, sticking with the notion that these are large fractions, well, to add and subtract them, we have to treat them just like we would numeric fractions. And that means getting a common denominator. Really, we talked about how when we multiplied and divided these rational expressions, that it was like trains, where we set up all our train cars and then just hook them up and see if anything cancels. These are more like accordions. So we're still going to factor them, but then we need to really expand the expression out once we know what the common denominator is. We're going to multiply in a bunch of things into certain fractions to establish that common denominator, and then that's like letting air into the accordion, and then once we bring it all together with our common denominator, then we can play the accordion and squeeze it back together, simplify everything. So this rule refresher slide is just reminding us that to add or subtract fractions, we need to have a common denominator. If we do have a common denominator, then we just add up the numerators all over that common denominator. Then the next little heading down there, if we don't have common denominators, then we need to adjust the fractions in order to set up that common denominator. That means finding the least common multiple between both of those denominators that we start with. And then lastly, what we're going to cover is simplifying complex fractions. Those are fractions within other fractions, and I'm going to strongly encourage that we choose method 2 for that, just because it's so much easier to take this in one swoop by getting a least common denominator for everything and then simplifying at once. You can see when we read method 1, it says simplify numerator and denominator, then divide. Well, that's a lot of work. We have to simplify twice and then multiply by the reciprocal. It's much more efficient, I think, to do method 2. But just know that both methods are available. In this video, I'm going to cover method 2 exclusively. I feel that strongly that it's the best method. So here I've broken it down into steps like we had before. The process when we're adding and subtracting. Step 1, just like before, we want to factor everything. And if there are terms that simplify, we should take care of that. Then we find our least common denominator. What's the least common multiple between denominators that we have? And then we're going to do step 3, which is multiply each fraction individually. And we may have to adjust them differently based on what they currently have in their denominator. And then we're just basically setting up all of our common denominators. Then finally add and subtract the numerators all over this common denominator. Now, you've heard me talk for quite a bit about it. I think an example is probably the best way to get started with this. So first, for problem number 6, you can see that we already have a common denominator in place. So it's just a matter of carrying out that addition, in this case, all over the common denominator. And we could factor and simplify it. We can look at this and see that, all I could take out is a GCF of 3x, and we'd be left with x plus 2. And that does not cancel out our denominator, so this would be our simplified answer. For number 8, again, we already have a common denominator. So we will add our numerators together over that common denominator. And again, let's see if anything simplifies here. Numerator is a difference of perfect squares. And so we do get a factor to cancel, and the result is simply 2x plus 1. All right, example 2, now kind of prep work for if we do not have common denominators. Find the least common multiple so that we have to do the least amount of work when we set up our common denominators. Okay, well, let's see. This 2x squared is a 2 times x, and this 4x plus 12, that's a binomial. All I can do is take a GCF of 4 out, and I'm left with x plus 3. So I need to gather all the factors here and see what they have in common and what they do not. So here I can tell that they both have a factor of 2, but the least common multiple I see is a 4. Now we had 2 loose x's multiplied in. and we had an x plus 3 multiplied in. So here is our least common multiple. If we had multiple fractions that we were adding up and they had these as denominators, this would be our least common denominator. Let's try number 14. Okay, all factored out, I've got a difference of perfect squares. That's 3x plus 4, 3x minus 4. And then to factor out this trinomial over here, well, I've got 3 times negative 4, negative 12. Magic number is there that multiply to be negative 12, add up to positive 1. That's negative 3 and positive 4. Got to put them over my lead term, or my leading coefficient of 3, and simplify. And this one doesn't simplify on the right. Factored out, I have 3x plus 4, and then I have an x minus 1. I apologize, I'm using a tablet here, and it's not quite the same as the old smartboard. X minus 1. All right, so now, what's our least common multiple? Well, when I look at both these together, I've got a 3x plus 4 factor, and both of them have that. I've got a 3x minus 4 factor, and then the bottom one had an x minus 1 factor, so need to multiply that in. Least common multiple. There we go. All right, so now let's put that into practice here. Number 22, you can see we are trying to add up these two rational expressions. And I just want to look at the denominators here because I cannot add them as I see them right here because I have two different denominators. So here we're going to have to multiply in to each fraction. We're going to have to make an adjustment before we can add them up. So here, this fraction right here, its denominator is only x minus 3. I need to multiply in this x plus 1. And I can't just multiply it into the denominator. I have to multiply top and bottom by x plus 1. Otherwise, it's changing that fraction's value. So that fraction becomes 9 times x plus 1 all over x plus 1 times x minus 3. Plus, now my second fraction, it has the x plus 1 in its denominator. It has that factor already. I need to multiply in the x minus 3. And again, I need to do that in the numerator and denominator so I don't change the value of the fraction. It's really just multiplying by 1. That becomes 2x times x minus 3 all over x plus 1 times x minus 3. Now I've got my common denominator. I know that I can establish one big fraction over that common denominator. And I'm just going to distribute and combine like terms. This will be a little bit of scratch work off to the side. I've got 9x plus 9, and then 2x squared minus 6x. All right, so let's put that all together here. I've got 2x squared plus 3x plus 9. And just to be sure that this is the simplified version of the answer, let's go ahead and factor out this new numerator that we've come up with and see what we get. Maybe we get a factor to cancel here. I'm not sure. Well, 2 times 9 is going to be 18. And magic numbers that multiply to be positive 18 and add up to positive 3, it doesn't happen. So we cannot factor this numerator. This is our final answer. For number 24, here you can see that, hey, we've got some factoring to do from the onset before we can start setting up those common denominators. So I'm just going to, right underneath the original denominator in this first fraction, I'm going to put x plus 7 times x minus 2. I'm going to factor that out. And that just clearly shows me what I need to multiply in. So you can see this has x plus 7. Well, the other one has x plus 7. This one has x minus 2. The other one does not have that. So I need to multiply in that factor of x minus 2. And again, multiply that into numerator and denominator. And then we'll go to work. We have our common denominators. We did not have to adjust the one on the left because it already had the x plus 7. All right, so now they both have the same denominator. Let's see what we get. I got x squared minus 5. And then here I want to be careful. I want to show that there's a minus sign here. And then I'm going to have x plus 3 times x minus 2. Whenever there's subtraction, I'm really careful about parentheses. This is all going to FOIL together, but a negative will distribute to all of it. I want to be sure I don't lose that. Then that common denominator was x plus 7 times x minus 2. All right, so setting that up isn't really terribly difficult. Let's see what happened if I FOILed these together. I'd get x squared plus x minus 6. And now let's distribute this negative and combine our like terms. So I've got x squared minus x squared. Well, those cancel out. Then I've got my x left over, but that negative is distributing to it. And then I have negative 5 minus negative 6. That's like plus 6. Combine those together, I get plus 1. All over that common denominator we had. And you can see we don't have any factors that cancel, so this is our final answer. One thing you will not see me do is FOIL together the denominator. We worked so hard to factor that up above. It's nice to leave this factored out, because that way when we do combine the terms in our numerator, then we've got something to factor in that we're looking to see cancel out. So definitely don't FOIL these back together. You're going to make a lot more work for yourself. All right, here we've got addition and subtraction of 3 rational expressions. Well, let's factor anything and everything that we can. We got to figure out what we might need to do for adjustments to multiply in and establish our common denominator. We got a difference of squares. All right, now this has x minus 5 and x plus 5. I also noticed the denominator of x plus 3, so I'm going to have to multiply in an x plus 3 into the numerator and denominator. In the middle, I've got x minus 5. I need to multiply in an x plus 5 and the x plus 3. Yeah, I want that denominator to be common among all 3 fractions that I'm adding up. And then lastly, I'm missing the x minus 5 and the x plus 5. So we have to multiply in multiple features to get our common denominator set up. All right, we're going to lay out a massive fraction here. You can see why this is an awful lot like expanding an accordion before you play a note. There's our common denominator. Well, let's see what we get. I've got x plus 3 times x plus 3. And again, this is just scratch work here. That's going to make x squared plus 6x plus 9. Then I've got minus x plus 3 times x plus 5 times x minus 1. Oi, oi, oi. We're going to have to definitely do some work off to the side for that. And then lastly, I've got plus 3 times x minus 5 times x plus 5. Well, that's going to be x squared minus 25. All right, so let's tackle this off to the right here. Well, x plus 3 times x plus 5, there's going to be a negative out in front of that term. That's going to make x squared plus 8x plus 15. And I'm going to multiply in an x minus 1. And if I carry that out, let's see, I'll have x cubed plus 8x squared plus 15x, I'm just distributing, minus x squared minus 8x minus 15. And if I combine like terms, I'll have x cubed and then plus 7x squared plus 7x minus 15. All right, and this of course will be 3x squared minus 75. So we begin the arduous task of combining all of these like terms. Well, we're just going to kind of seek these things out. I'm going to have a negative x cubed. And now let's find all of our x squared terms. I've got positive 1x squared, positive 3x squared, and negative 7x squared. Positive 1, positive 3, negative 7, that's minus 4x squared. Okay, so all those x squareds are accounted for. Now let's look for x terms. I got plus 6, none coming out of this work, and then a minus 7. So that makes minus 1x. And then lastly, our constants. I've got plus 9, I've got negative 75, and I have positive 15. Let's see, negative 75 and positive 15, that's going to make negative 60, and then plus 9 is going to be negative 51. All right, now it's pretty clear to me that the only way we could factor this to maybe get a cancellation is by grouping, and by looking at the coefficients I can tell that that's just not possible. So this is our final answer. I'm just going to do one thing to clean it up. I'm going to pull the negatives out of that numerator, undistribute them, and you may notice that textbooks will do this from time to time. It just makes the answer a lot cleaner, a lot easier to work with. If we had to turn around and plug an x value in or type this into a calculator, this would be a much cleaner answer than the one up above. But there we have it. Yikes. Nice example. Okay, for our next trick, we're going to simplify the complex fraction. And remember, we're looking for the least common denominator among every fraction involved. This is where that method 2 comes into play. So I'm going to look at these constants as being over 1. And then what do I see in my denominators? I've got a x and I've got a 5. So that means for each piece of both numerator and denominator, I want to make them all over 5x in this case, to get the common denominator among all 4 of these terms. So I need to multiply this fraction by 5 over 5, this one by 5x over 5x, this one down here by x over x, and this one over here by 5x over 5x. What does that set up? Well, now I've got a common denominator across my numerator. 5x times 15 is 75x. Negative 2 times 5 is negative 10. Again, that's all over the common denominator of 5x. In the denominator, I've got an x squared plus 20x, all over that common denominator of 5x. And you really, when it comes down to it, you're not going to have to show this step, because when I have a fraction divided by another fraction and they have the same denominator, think about what would happen if we multiplied by the reciprocal. Well, if I multiply by the reciprocal, I'm going to have 5x over something, so those 5x's are going to cancel out. So here's why method 2 is so much nicer. We get 75x minus 10 all over x squared minus 20x instantly. And again, we may want to factor that out. In the numerator, I can take out a GCF of 5, and I have, let's see, 15x minus 2. And in the denominator, here I can take out a GCF of x, and I'm left with x minus 20. So nothing cancels, but we do get a glimpse at how we could simplify our answer if necessary. You should not have to simplify if you use method 2. However, if you use method 1, you may have to simplify more than not. And that is if these fractions are already in simplest form when the problem's given to you. But again, method 2, pretty slick. I think we'll have another example of that coming up. Yes, we do. So for number 44 here, notice that here we have an x minus 2 times x plus 2. I'm going to factor anything and everything first, and that appears to be my greatest denominator. Well, this fraction that's also in the numerator only has x minus 2, so I need to multiply in x plus 2 on itself to establish that common denominator. And here I need x minus 2, because it already has an x plus 2 in its denominator. And here we need to multiply in x plus 2 times x plus 2, or over x plus 2, I should say. Okay, so we have established that we have got our common denominator. I'm going to show you how we can jump right to a single fraction. And this is the real beauty of method 2. So in the numerator, I'm going to have to distribute this 3. I will get 3x plus 6, and then minus 6, all over. I know this top part of my gigantic fraction is going to have the same denominator as the bottom, so I know they're going to cancel out. In the denominator, I will have 3x minus 6, again, just distributing, plus x plus 2. So very quickly we get a lot of that to cancel out just by using method 2. My numerator is down to just 3x. And my denominator is going to be 3x plus x, that's 4x, and minus 4. And pretty obvious from there that we will not be able to get a factor to cancel out, but again, very quickly see how that method 2 is super nice, very efficient. And our final example, a word problem here, we have a formula here for the total resistance of two resistors in a parallel circuit is given by this equation. Simplify the complex fraction, then find the total resistance when R1 is 2000 and R2 is 5600. Now obviously, if we were just tasked with the second part, we could plug in our 2000 and our 5600 and just let a calculator do the work. But you can see this is kind of a complicated formula even to type something into a calculator with. So what we want to do is treat this like a fraction within a fraction. So the numerator, I'm going to call that 1 over 1. It has a denominator too, even though we can't see it. We've got our big divide and then our denominator. Well, I need to multiply in R2 down here and R1 over R1 here to get a common denominator there. And remember, I want the common denominator to be among all pieces of this fraction, so I need to multiply the numerator by R2 R1 over R2 R1. It needs both pieces of that denominator. So now what's left? Well, R2 R1 is what I have when I multiply across numerators up above, and remember that denominator is going to cancel. So then I have my big divide, and in the denominator I've got R2 plus R1. So there's our simplified fraction. You can see much easier to work with if we have numeric values to plug in. So here's what's going into our calculator. 5600 times 2000 over 5600 plus 2000. All right, and we'll take a second to type that into the calculator. Actually, got to get mine out of the drawer here. And what I get as an answer is 1473.68. Tablet. Okay, and that's the resistance in ohms. They do specify units. We should do that. And just for kicks, I'm going to type in that 5600 and 2000 into the original problem just to see if I get the same answer. So I've got 1 divided by, and I'm going to use some fractions here, 1 over 2000 plus 1 over 5600. And I get the same exact answer, 1473.68. All right, so that does it for this section, 7.4 on adding and subtracting rational expressions. Here's a look at your assignment.